Hello, everyone. My name is Amy Chow, and I'm the Sales and Marketing Representative for OrthoTool. Along with Doctors Edward and Theodore Chow, I would like to welcome you all today for joining us. Our webinar will be exploring the custom design approach to myopia management, and we want to shed some light on the mechanics of myopia treatment and demystify design principles behind Ortho-K lenses. OrthoTool has actually been around for over 20 years and marries the technical sophistication of the software with practical clinical experience for targeted results. So without further ado, here's Dr. Chow.
Hello, good evening. Eddie Chow here. Good evening for people in Canada and North America, and also good morning for the doctor in Australia, my friend Oliver and Gavin, and also Hong Kong, Singapore, China, and also doctor from Europe. So this, thank you for joining me, and you'll have a wonderful evening. I want to call this webinar a roll from mysteries, obstacle, and hardship to success with OrthoTool. I've been dealing with orthokeratology for over 40 years and going through all this hardship, black box, and designing lenses, and a lot of trouble. And all through this year, I never gave up, and eventually I make myself very successful in this in the design. So I hope by the end of this presentation, you will find out that the procedure is quite simple.
Good evening, colleagues. I'm Teddy. Thanks for allowing me to speak with you and kind of join with Dr. Chow and to share my junior perspective with my experiences with OrthoTool. So to me, OrthoTool is an educational software more so. It has helped me familiarize myself with a lot of the building blocks involved with contact lens designs. It's sort of like getting familiar with all the Tetris blocks and seeing how they all fit together, how rotating one Tetris block will, or changing one curve will influence the other curves and the whole system. I've had quite a bit of time during lockdown, and playing with OrthoTool has really helped with the why and the how of Ortho-K lens design. So I'm excited to share with Dr. Chow.
So now, OrthoTool has been designed based on the following: the hydrodynamic principle, a fluid dynamic force, the sex philosophy to control how the lens sits on the eye, and most important is the control clearance, a design concept that calculates the peripheral curve system relative to the patient's cornea to create precisely control bearing area, tear reservoirs, and edge profile to create a balanced fluid force under the lens.
So you can see here, this is your OrthoTool online platform. The preferences focuses a lot on the tier layer thickness here. So whether that be right in the center, the apex, the tier layer thickness here, at the junction here, it focuses a lot on tier layer thicknesses. And for me, this was very helpful in providing a different perspective when looking at reverse geometry lenses. Historically, I was trained on focusing on, the Jessen factor, that overcorrection factor, going greater than the patient's RX for determining how to adjust treatment effect sizes and forces. With OrthoTool, there's a little bit greater focus on the amount of tiers behind each of the zones of the lens and how the differential tier volume across these zones, how that influences treatment effect.
Yeah, so OrthoTool is designed based on numeric numbers, so you can tell exactly the tier volume under each junction or each area.
So here's the hydraulic model that was introduced way back by Hayashi and Roger Tabb, a fellow optometrist, back in the 80s. So what it describes is, in the closed eye condition, the total forces acting on the cornea lens system is this positive push force and this negative pull force. So The positive force is compressive, and the source of is the lid. And this is critical. It has to have a contact lens. They used initially a 0.25 millimeter thickness lens, but that's critical. And these two together create a constant force. And we don't change this. We don't change this force. What we do is, with the contact lens design, is change the negative pull force. That's the squeeze film forces. And the source I'll elaborate on later is mainly the differential between the peak TLT here at the edge of the optic zone diameter and the apex right here, this minimum TLT. So this difference creates the main tension force. And the combination of these positive and negative forces creates that push-pull mechanism that you may have heard of. It's this push-pull mechanism that creates tangential stress on the epithelium. And this tangential stress causes intracellular fluid contents to flow, as if the intracellular contents of cytoplasm is a Newtonian fluid, basically moving with that tangential stress. And so you have that thinning and the mid-peripheral thickening of the epithelium. Now, importantly, neither compression nor tension alone is sufficient to cause tangential stress on the epithelium.
So for many years, I've been talking about tissue movement, but now you understand that there's no tissue movement, but only fluid transfer. In the meantime, I want to tell you the phenomena of grade and raisins. So before molding, fluid volume can be considered a grape with a lot of fluid inside it. And after molding, the fluid loss will turn the grape into a raisin, providing more space at the peripheral, mid-peripheral region. So you have to proper adjustment of this curve for proper force.
So this is a model Conway back in again the 80s expanded on the model by using this tension force formula. And the most important part of this formula is this alpha value right here. This alpha value, I think called the clearance factor by Don Nowak, is defined as the difference between that peak tier layer here, that peak here, and that minimum apical clearance right here. So this differential is the main generator of the tension force. The greater the tension force, the greater the difference in the push-pull mechanism, the greater the tangential force, and the more you have epithelial flow. So, as mentioned earlier, the control clearance philosophy focuses on finding the ideal tier layer behind the lens to optimize these forces. Now, traditionally, one can hold the apical TLT constant, and then you modify the peak TLT here. That's typically the Jessen method. The Jessen factor increases the flatness of the back optic zone radius, and you increase this area here. The second method is keeping this max TLT constant and then changing the apical clearance. I believe this philosophy was used by John Mountford with his BE retainer lens. Now, the beauty of OrthoTool is you can do both. You can keep one constant and change the other, or you can change both. You can experiment with all variations to fit your patient's needs. So before I introduce biomechanics, I want to quote John Mountford. He mentioned orthokeratology is complex. He had this philosophy that simplistic solutions to complex problems result in errors. Now, as a young practitioner, I feel that the potential for a true, consistent first fit success is disconnected with the reality of how complex the ortho case system really is, from your lens design to your corneal physiology to the tier layer forces in between. So this may be why we still see so much inter and in fact intra-individual differences with ortho-K fitting. Corneal biomechanics is a recent advance that adds a layer of complexity. Very briefly, viscoelasticity is the property of human tissue. This is for the cornea, that's Bowman's and stroma, to have the ability to be elastic, but also viscosity, so it can absorb and dissipate forces as well. The two parameters that we use to measure biomechanics is the rigidity factor and the corneal hysteresis. Rigidity is weighted towards elasticity, hysteresis weighted towards viscosity. Both include the other, but it's weighted more towards one parameter. So myopes were found to have a low hysteresis. Their ability to absorb forces was much less, and this was associated with a longer axial length. They were also softer, where they had a greater deformation. You can see the cornea deforming here. Incidentally, I think this may be a keratoconic patient. But certainly the myopes were softer than the hyperopes. Now, with ortho-K, there's a lot of theories, all related to how rapid the response is, how rapid the regression is, how stable, how much force we need to put on.
So there's no, not everybody can have a machine called ORA to measure the CH-CRF. So the center thickness of the cornea is very important, since it is corresponding to corneal resistance force, the CRF, to tell you the rigidity versus the soft cornea. So one thing to remember is the CRF, CH will change, and also the CCT will change after molding. Then you have to determine the topographer map and fitting after molding. So now, I call this 8+ curve OK lens design, which is a US patent for myopia management. So you can have the base curve, which is a sphere or a sphere, and a reverse zone, and 2 relief curve. I only use 1 most of the time, and 2 alignment curve and a peripheral curve. So most of the doctor and the lab will not mention about the front geometry. Actually, the front surface geometry is also important. The front curve has been calculated by the software to match the back surface of the lens for harmony, to allow the best configuration of junction thickness, fringe, and edge profile for comfort. This is very important, especially for Asian kids with tight lid. You want to have a very comfortable fit of lens that they don't complain too much.
This is a short video that goes through how the user can adjust each of the lens curves on the OrthoTool platform. So going from the apex, the center, we will go through in each of these curves in detail and how, and then the why in the following slides. Suffice it to say, there's a tremendous potential for customization. At first, that level of customization triggered a little freak out moment when I first played with OrthoTool, and thankfully it's not nearly as intimidating as a quote complete custom design contact lens sounds. The OrthoTool software, its own algorithm, uses the control clearance philosophy to give you a starting baseline lens after you enter in the patient's refractive status, their corneal topography, eccentricity. From here, you can adjust as you like. Such as very simply changing the Jessen factor, or then using advanced changes. As you can see here, we're playing with the relief curve TLT.
So now, for many, many years, orthokeratology is only the advanced and custom design. And a lot of doctors were saying that, oh, there's a lot of learning curve, very difficult to follow and get confused. So last year, I designed a basic semi-empirical. So the basic design helped a lot of young doctor, beginners to get into this orthokeratology practice with good result. So my basic empirical design between the range of -1 to -5, you can achieve more than 80% success on the first fit. On top of that, there's the custom GP design, traditional GP with bitoric, a spheric multifocal for myopia management, and hyperopic orthokeratology. So I don't really like to design lenses in a black box. So a minor changes make it easier. You still can change some curves, such as the overall diameter, base ozone diameter, Jackson factor, the target power and flat power, eccentricity of the cornea to match AC width and radii, compression factor to adjust force required. less complicated and easy to design. You can achieve good results. So now, when you design a lens, there's many steps. What is the most important step? First step, or so, I have for success, I have classified into 9 different steps. The first one is the overall diameter. So the overall diameter is very important. Is to construct the best framework. So when you're building a house, you need to know the size of the house before you can buy furniture, the size of the furniture, the amount of furniture. Without having the best framework to start out with, is very difficult. So you can determine the diameter by measuring the HVID using topographer or ruler, or choose diameter approximately 0.2 to 0.8 millimeters smaller. The way I do it for many, many years, I like to visualize the fluorescent pattern evaluation with the lenses on. So trial fitting, to save you chair time, to give you a more basic knowledge of what is supposed to be the building block of the alignment curve. Ideally, biggest allowable overall diameter allow for proper containment of all necessary curve, allow the alignment curve to cover as much area as possible for effective centering and force application. So now, sometimes you get into trouble. You have a small cornea, let's say 10.4 millimeter or smaller, that you have to go larger, sometimes over the superior limbal area, that you have to adjust the peripheral curve TLT, that you can do it yourself to avoid encroachment at the limbus. And with the help of the front geometry of the lenses, the French and junction thickness can be reduced for more comfortable fit. The center part is the ideal size. Hopefully you have a round shaped cornea, but in case you have an oval shaped cornea, then what are you going to do? In this case, there's room for making it larger, but it's already over the limbal area and is superior. With oval cornea, go slightly smaller with the diameter, but compensate with extra force in the alignment curve, stiffen it up to increase AC width to improve stability. So this picture is the design, is the research from Weinstein and Bloom. They are measuring with topographer the corneal epithelial thickness. We find out that the epithelium is significantly thicker inferiorly than superiorly, thicker nasally than temporally. So you have to apply a larger diameter to cover more area, or else the lens will cause decentration. So the next one is the topographer, understanding of the topographer and trial fitting. So it's very important to understand the topographer, and sometimes you cannot trust the E value they provide. In this case, they have a low shape factor in the center, but high E value towards the peripheral. So proper evaluation of corneal shape to assist lens design is very important. So when you look at this picture on the right side, you have a very low shape factor. The E value is 0.29, and by trial fitting the patient, the flat K is 42, and the alignment curve 1 is also 42. We're fitting on K, and the left picture is misleading to some point. There's an E value of 0.91, but actually the central part is very low with low shape factor. So you have to be careful. Trial fitting is more important. So when you deal with this displaced apex, this is the 45 years old patient that came 6 months ago, and well, I have to put in different trial lenses to find the best. A trial fitting is a must in this case. Find an AC that show 360-degree dark band with slight movement to find out the proper alignment curve. So this is to show you how to evaluate the proper lens on the eye. The trial fitting allows you to visualize the actual lens positioning on the eye for each individual patient, especially for the Asian kids with small fissure and tight lid. And you have to hold the lid to let the fluid drain away. To show that a slight tight fit. The horizontal diameter can be slightly larger. The vertical diameter is normal, but with an increase in total diameter, edge profile has to be adjusted. So the third one, also very important, is choose the alignment curve. So when you're building a house, you need a very solid foundation. When you're building a house, a building of 10, 20 story, you especially require a solid foundation, especially with high targeting. So the alignment curve is the first curve to be determined. The landing zone is the landing zone, provide lens movement and assist centration, provide capillary force that will help stabilize as well as push tissue from the edge and build it up at the reverse curve. On top of the capillary force, they also have the compression force and the surface tension forces. You fit as tight as possible. You don't have to worry because there's 3 micron of natural tear on the eye already.
I just want to add that one of the greatest advances during the early iterations of Ortho-K designs was widening of the alignment curve to 1 millimeter or greater. These are the default values now, 0.9. So initially, I think it was either Jim Day or Tom Ream that split up the AC1 and AC2. But this 1.5 value here, that large alignment curve was historically very helpful with lens centration. And in fact, when you look at the capillary force, the more surface area you have of contact between the lens and the cornea that matches, the greater the stability. That capillary force is one of the reasons why just regular aspheric back designs of GP lenses fit so well on corneas.
So one thing to add is, if you choose the proper alignment curve and the diameter, you're almost 50% to success.
This is just very briefly, John Mountford calculated the expected starting point for the alignment curve to match different eccentricities of cornea. We know that with the greater eccentricity, the cornea will flatten faster from the center to the mid-periphery, to the landing area. And historically, I think they had just a very small range, fit a quarter, 3/4 flatter than K. But you can see, in fact, that it's quite a large range from a quarter to even over 3 diopters. I have yet to fit many patients to really give a lot of input, but what I can say is this: Dr. Chow mentioned the importance of trial lens fitting. This is clear why trial lens fitting is so important. However, the other thing it points out is the importance of having a very accurate and very precise topographer to be able to have an accurate eccentricity value if you cannot or will not do trial lens fitting. So having a good topographer is critical.
So now, designing of the trial lenses. So it's always standard at the AC from 8.54 to 7.50. You can target whatever power you like, -250, -5, -650. You can design your own lenses, or you can ask me to design for you. And the left have 3 different set of trial set for sale. So again, the largest possible diameter to match optical and reserve zone area within the desired lens diameter. AC1 and 2 width depending on fitting condition and forcing pattern under lenses. So there's something to a trick to tell you that if you use AC1 larger than AC2, is going to have tightened the fit. With AC2 larger than AC1 in width, to loosen the fit a little bit. Fine tuning is necessary in some cases. So the fourth to determine is the back optical zone diameter. So this is very important because the optical zone diameter will compose of an important feature in terms of myopia management. This is based on pupil diameter in room and dim illumination. And in my opinion, it is independent of our RX targeted. So if you are targeted at -1 or -8, you're still using the same desired optical zone diameter. For adult with larger pupil size in dim illumination, size can be increased, normally between 5.0 to 6.0, with an average mostly used is 5.4, and the most 90% of the back optical zone diameter I use is 5.2, 5.4, and 5.6. I try to narrow down the choices so you don't get into confusion.
Just want to talk about peripheral defocus theory. Is now popular, very popular theory of emmetropization now. The whole idea behind changing the back optic zone diameter, I feel, comes from this theory. Just very briefly, you have this prolate globe, this orange, this myope. This prolate globe causes a hyperopic focus of this image in the mid-periphery. And this hyperopic image, I love this article because it shows very clearly that you have a thinning. That purple is the choroid, and you have a thinning of the choroid. This precedes axial elongation for that retina to match, emmetropize to match that hyperopic image. The reverse is true with the hyperope, and you have a thickening of the choroid. So then, knowing that these peripheral retinal optics plays a large role in emmetropization, how can we capitalize on this? How can we capitalize and manipulate the optics going into the pupil to optimize the image hitting the mid-peripheral retina?
So now we want to induce myopic defocus. Many years ago, we have this result. Look at the topographer on the right side with -1. The result is very good, 20/20 in the morning, throughout the day. But look at the red zone, it's not enough. So I build it up more. Is it enough? No, you want to have even more. We'll talk about later. So by building up the mid-peripheral red zone, you also have to remember also to provide a clear central vision.
So Dr. Chow was referencing a -1 in the top left here. This is a -1 myope, and look at that red ring there. So the red ring is that peripheral myopic defocus, us manipulating the mid-peripheral optics. This is a -4. The profile, you still see that ring, but it's much nicer. It's very, very different. This is courtesy of Professor Caroline, and what we see here is that compared to a LASIK patient, the treatment zone, this area here, is typically 1.5 to 2.5 millimeters, very small. This is a good thing because this allows for that peripheral plus. This is the pupil size. It allows for that peripheral plus near the pupillary edge. And then you have this V shape here, which is related to the positive spherical aberration that we'll talk about later. So the pupil size, comparing LASIK with a very large treatment zone, a 6 millimeter optic zone ortho K design, and a 5 millimeter optic zone. Notice how the treatment zones get smaller. Notice how the V shape gets more prominent. The two major theories of myopia management is this peripheral plus right at that pupillary edge and that positive spherical aberration that is given by this V shape, this small treatment zone, and steadily increasing plus power towards the pupillary margin. Peter Chen did a study where he looked at the pupillary diameter in various children wearing Ortho-K and then looked and found that axial growth was significantly slower in the children that had large pupil sizes. Now, their theory is that this larger pupil allows for more of that peripheral optics, that myopic defocus and positive spherical aberration to squeeze into the pupil and reach that mid-peripheral retina. And that's a great theory because we can really capitalize on that with contact lens design. We can really, depending on the patient's pupil size, if it's very small, we can focus on a much smaller optic zone to squeeze in all those optics inside the pupil.
So you can also say that in a LASIK patient that the myopia defocus is almost zero.
This is a proof in principle. This is also courtesy of Pat Caroline. On the right, you have a myopia control focus. The smaller optic zone is reflected in this topography. Very nice small red ring here that's really jam-packed into the pupillary zone. So the problem, going back to that -1 patient, if you ignore this first, the -1 patient, if we put them in a spherical design, that spherical design doesn't really create a sufficient max TLT. So this is the max TLT with a 6 millimeter with a 5.4. Notice when you go from 6 to 5.4, look how small that max TLT is. Remember the clearance factor, the difference between the max and the minimum is related to the forces. There's not a significant amount of force if you have a small myope with a spherical design. What can we do? We can change and incorporate an aspheric design. An aspheric design will push up that max TLT, and you can manipulate the forces that way. So what is the spherical versus aspherical design and why it's important?
So now look at this picture from Professor Caroline. So the average myopia control rate is 48.8% and less than 50%. What has gone wrong? Do we want to improve the myopia control result? Are we using the proper design? So we'll talk about in the following slides. So now I have two studies. The study one using spherical 6.0 optical zone design, and you can see that for low myopia, -3, -2, and 1, so the axial elongation is a lot. Not until you go to -5, then the result is better. So my second study using spherical 5.4 ozone design, the result is a lot better. So for -1 myope, we don't want to target at -5 for result, and result in +4 in the morning. What can we do to avoid that?
So aspheric curves, there's a rule, also courtesy of Pat Caroline, this rule that the amount of peripheral plus power that we get at the pupillary margin at 5 millimeters is equal to the central minus power corrected. There's this 1-to-1 ratio. So you can see in this -1 diopter myope, the peripheral plus at 5 millimeters is +1. Now, how can we break this rule? This is just a very brief brush up on aspheric curves. The green is a spherical back optic zone. The cornea is the dark red, is a prolate ellipse. When you fit, and then the blue is an aspheric, E is greater than 1.0. Look at the green, you see the clearance here between the red and the green spherical, and then notice how with an aspheric back optic zone, as we move from apex to the edge of the optic zone diameter, you really get a really fast flattening, and that's where you have this increase in the max TLT afforded by that aspheric curve. So we break the 1-to-1 rule. Look at this this design here. We start with a spherical design. This is a -1 diopter. Look how small it is. 1.4, you see the max TLT goes up. 1.6, even more, it goes up. And so you really can change that, clearance factor with an A-sphere curve, especially with low myopes. And this is just another way to look at it. With a spherical design, that peak TLT is reached at 5.3 millimeters, 50 microns, but with an aspheric, that 50 microns is reached much earlier.
So now, when we talk about the 7.5 correction, for a 4 millimeter pupil size, you have a +4 diopter edge. For 6 millimeter optical zone size, the peripheral edge is +9.5, so it's less than double. Is it enough for myopia management? So with my study, this patient with -6 diopter of myopia, 5.4 millimeter base optical zone, and you can tell the strong red ring. This picture shows an almost 20 diopter plus power at base optical zone of 5.4. It's almost 3 times extra plus. So we need to have the plus is not 1 to 1, not 1 to 2, not double, but 3 times or as much as possible.
So the one danger, this diagram here shows one of the dangers of having an aspheric curve. Because it flattens so fast, if you have a large optic zone, you're really allowing that back optic zone to flatten out. And you look at that 6 millimeter, it flattens out really well. And the peak there is almost 100 microns. So the danger is the larger the peak, the greater the forces, and you come into a lot of issues with perhaps excessive forces. The lens will sag down onto the cornea. That's one of the things that we have to consider when we have large optic zones, especially with high myopes and with high eccentricity. Dr. Chow likes to have this standard. This is his rule where, depending on the optic zone diameter, he changes the starting default with the E value.
So with a small base optical zone diameter, 5 millimeter, you can go 1.6 and above, and up to 2. And for larger diameter, say 5.2, you use 1.6 or more. 5.4 is the default value, is 1.4. When you get larger, they go less, So 5.6 is 1.2, and 5.8 and 6 is 1 or less than 1. So apply higher E value only with small base optical zones. That's why that we can incorporate higher E value. That's why we want to make the optical zone smaller to accommodate for high E value. Exception is with higher E value allow with wider reverse curve. Aspheric can be increased up to 2 with a wider reverse curve width. Vary with corneal rigidity. Higher the rigidity, you can apply higher aspheric. Rigidity change after molding, so monitor carefully with topographer. So now this is the picture that I figured out myself. Doctor was asking, hey, what is the pupil optical zone? What is the treatment zone? So to my understanding, we want to have a V-shaped, very small treatment zone. A small treatment zone allows concentrate light going into the eye for clear, sharp central vision, or V shape. And the optical zone is the back optical zone diameter. Aspheric back optical zone allow diffuse light going into the eye to avoid mixed astigmatism for quality vision. This is also verified by Professor Smith in his defocus theory, that the mixed astigmatism, I truly believe that can be eliminated to some extent by aspheric back optical zone. So now, final conclusion is the ideal shape profile with a very small optical zone and enough area for alignment curve to embrace the eyeball for solid foundation. So now we're talking about the base curve radius.
Typically, this is the Jessen factor is one of the first things that I remember learning about Ortho-K in school. It usually, I think, 0.5, 0.75 over the target RX. Pauline Cho and John Mountford released a paper in 2008 that suggested it, and this was the Chinese population, that this 0.75 was invalid. It was an underestimation of the daytime regression, and actually they wanted to go much higher. Now, so the study used the E-lens, I believe, a 6mm spherical lens. So it may not be an accurate reflection of the forces across the wide variety of lenses out in the market today. That means I don't believe that there is a true hard set Jessen factor. I think it's a range. I think we can start low to avoid too much forces, and we can add always in the future, so maybe from 0.5, 0.75 up until +2.
But in my experience, for young kids, as long as they have good accommodation, they can stand higher plus power. My usually ranges from +2 to +250. So my design is a little bit more aggressive. So another thing is always maintain the lens RX from +2 to +250. You don't want to have something more than that, say +3, +4. Then the lens will go too thick, since it will affect the lens thickness. To check the actual target required, over refraction with lens on to determine over and under correction or amount of regression. Refraction without lenses determine current RX to increase or reduce targeting, adjust the power for desired amount. You can target over 3 diopter depending on CCT, the corneal rigidity, and the amount of regression upon treatment. If your initial treatment, the flat power is +250 at dispensing, over refraction should be 0. After treatment, say 2 weeks, over refraction with lens on is -1. That means there's a regression of 1 diopter. So now the most important curve now. We have to put in all the other curves. Then we figured out what is the reverse curve and the relief curve.
So the reverse zone, it basically fundamentally it connects the edge of the back optic zone with the alignment curve. And so this region here, typically, I know Dr. Chow has an ideal. There we go. It's a 60 to 100 plus microns. Remember, this is the peak TLT that influences that alpha clearance factor. For me, historically, I know that these are the defaults, 0.5mm width. Again, historically, one of the biggest, most important changes in Ortho-K designs was when they narrowed the reverse curve width to, I think it was a 0.6mm. So these are the defaults. The relief curve allows for that really steep reverse curve to connect a little bit, transition a little bit better with the alignment curve. Now, we can change the reverse curve width. This is one of the unique things and one of the advanced changes that I'm still trying to understand. But when we increase the width, you're giving a lot more room for the edge of the optic zone to reach the alignment curve. So naturally, the reverse curve will flatten. This is an exponential change. If you decrease the reverse curve width by 0.1mm, you're really not giving a lot of room for the really flat base curve to connect with the alignment curve, so it steepens up a lot. Now, I know Dr. Chow always mentions that he needs to have the reverse curve radius to be greater than 6.0mm, as that's relevant to the ease of manufacture, I believe, but he'll comment on that himself.
So the comfortable zone for the upper limit of myopia control, so you have a flat K minus 40, a flat K and a -1, So for the effective myopia control, I find that, the upper limit is 6.6 millimeter. So anything above that, the result is not as good. If you go below 6 millimeter, then they'll be too tight. So the reverse curve width is actually is from a very small range. What I use most of the time is from 0.4 to 0.6, you know. So if you are targeting at over -5, you might go to 0.7, but most of the time the default value is 0.5.
So what the reverse curve does with typical lens design is it controls the overall sag of the lens, the sag height. So if you want to make that sag greater, you see here you're increasing the steepness. You're steepening the curve, and you're going to increase the sag. If you flatten the curve, you'll decrease it. And be very careful. You don't want to have 0 TLT at the apex, no ortho K effect. If it's too high, insufficient forces. So one way to adjust the apical clearance here is to change the reverse curve.
So now the change of the reverse curve radius, I mean the width is very important. If you change just 0.1 millimeter in width of the reverse curve, it's equal to 0.2 to 0.3 millimeter in radius. It's about 1.75 to 2.5 diameter. So it's a big changes. So most of the time you don't want to make such a big change. You can adjust the curve by minor adjustment with the base eccentricity, reverse curve, relief curve TLT. By changing this TLT and base eccentricity, the only change is 0.02 millimeter and is less than 0.25 diopter.
So I just want to add and plug in that when we're changing, reverse curve and relief curve to me is more advanced, and I'm still understanding the intricacies behind changing these curves and how it affects the lens overall. But do note that if you were to change one value, there will be an automatic subsequent optimization. So the software will optimize all the other curves to adjust accordingly with all the other curves that you changed. So this is a quick image of the relief curve zone, and the relief curve zone is just that transition between the reverse and the alignment curve. Dr. Chow has this philosophy where, you know, the clearance factor was the max and the minimum at the apex, but there's another minimum here at the relief area, and you can change the relief curve TLT to adjust the forces. If you have a very narrow, very thin TLT here between the reverse and the relief zone, theoretically it would be another minimum, and then you can adjust, fine-tune the forces this way.
So I make the range smaller. So most of the time it's 0.3. Only if you want to relieve more, then use 0.4. So the range small, then you don't get confused. 0.3 most of the time, and only you want to relieve more, you use the 0.4 millimeter relief zone width. So one thing to remind you is in order to fall into the category that the reverse curve radius should not be below 6.0 millimeter. So if you have a steep K, then you have to widen the reverse curve width by 1 millimeter. And if you have a flat K, say like 41, then you reduce the width by 0.1 millimeter to make sure that you are not have too much force or not enough force.
So just to walk through this diagram here, you start off with a very high prescription, a very steep K of 45. And you notice that, let's let the video reset. The reverse curve radius is 588. That's very steep. Increase the reverse curve width and you have 0.6. The reverse curve now is flattened. It's over 6.0 millimeters in Dr. Chow's comfort zone. What happened when you made that reverse curve from 0.5 to 0.6 is you had to take away from the base optic zone. So that 5.4 turned into 5.2. So then you have to change the alignment curve. You have to give it back by making the alignment curve width a little bit smaller. When that happens, you'll notice the final diagram has the same alpha level, the clearance factor is the same as the original 5.7, 5.8 radius, but at least the reverse curve is now over 6 with the same amount of forces between the maximum and the minimum. This is a very similar example, but I'm not going to go through it. It's with a very low myope and a very flat K. And so similar adjustments, but just in the opposite direction.
So now, Katie was talking about the dual forces, but now my dual forces is not the same. The dual forces is in this area, generating small capillary surface tension and squeeze stream force. So the incorporation of the relief curve is very, very important. They push the tissue from the edge all the way to the mid peripheral. And together with the suction force created by the shrink back optical zone, then you have the sufficient forces for myopia management, and also satisfy the sagittal height philosophy, because by adjusting it, the lens can be sitting lower or higher. So when you change the reverse curve width from 0.6 to 0.5, you create extra forces.
Now the peripheral curve is really quite simple. There's a standard. It ranges in the textbook. I've heard a range of 80 to 100 microns, and so Dr. Chow typically ranges between 60 to 90 microns. The width is typically 0.3. How we change it is actually quite simple. You don't have to actually change the peripheral curve radius. Instead, you can just adjust the TLT here. This is 90 microns, 75 microns. The software will then adjust your peripheral curve radius accordingly. I've heard many times that Dr. Chow likes to aim for a peripheral curve clearance that is the peak, that is about half of the peak TLT at the edge of the optic zone.
Yeah, so the peripheral curve width is always at 0.3. Only one time I used 0.4, but we want a tight lens, water sealed lenses. So the peripheral curve 0.3 width is enough, and the TLT you can adjust accordingly. So now I want to talk about this patient, limbo to limbo astigmatism. So do we need toric curve? Most of the doctor will say, why not? Definitely, 100%. But by looking at this patient, 7-year-old Asian boy, the flat K is 40.75. The myopia is -650. The cylinder is -4. So I never used the shirt, but using trial lens method and determine the AC is only quarter of diopter flatter than fat K, although the E value from topographer is 0.54.
That being said, I just want to point out that the OrthoTool software does have the option to create a peripheral, a toric peripheral curve. So this toricity here, which is beyond the scope of this webinar, but this toric curve will give you a different base curve, a reverse curve, and alignment curve.
So now this is what I call corneal sphericalization. So with the incorporation of the suction, small capillary and surface tension forces, no toric curve is necessary. The way I look at it is that if you use the toric curves, then it's harder for the lab to manufacture, and you don't know whether they make a mistake or not. And by using a toric curve, you're fitting the cornea instead of treating or molding the cornea.
And I just want to give my final thoughts, and then Dr. Chow can give his. So as a young practitioner, I clearly see that there are a tremendous number of design philosophies in Ortho-K. I've tried to look up many different designs, ranging from empirical to semi-custom to fully customizable. I'm excited to be able to use OrthoTool only as it is my blank canvas. It gives me the opportunity to mimic or play, have a design similar to others, and kind of understand which philosophy suits the patient. I feel that it might vary depending on the patient. Thank you. So
Ortho 2 design, although look complicated, but it is actually simple if you follow the rule, the default value. I make it very, very small, so I don't want to complicate all the doctors. For initial fit, the overall diameter, base octagon diameter, target power, apex TLT, and the alignment curve width and radius are quite standard, so you don't have to go too far to find out what's going on. The reverse and relief curve TLT is a little challenging, but if you follow the provided limit, it will not be too difficult. You need time to get familiar with the fit and how to judge the topography and mat properly. Once you are used to the low oryx and astigmatism, you will be capable to deal with more difficult cases. Personal consultation. I'm always around to help, ask those doctors, and 3 o'clock in the morning, I'm still designing lenses for the doctor. Personal consultation and online instruction will be available. Myself, my daughter Amy, and my son Teddy will also help out. So thank you and very much for attending. And you have questions, please send me an email. I'll answer your question personally. Amy. So this is also a cookbook that will be available online that classify and clarify all you want to know, and it's simple to understand.
So thank you all again for investing your time with us today. Please don't forget to submit all your questions, which we will answer individually. For any sales questions, to find out more about our webinar promo and how to certify, please contact me at sales@orthotool.com. Thank you.
thank you.
Thank you. Good evening.